Hello, hello. Hello, hello. Okay, it's audible, right? There is quite a bit of latency from where in between the recording and when the video goes live. Okay, it's audible, right? There is quite a bit of latency from where. Let me recording and when the video goes live. Okay, it's audible, right? There is quite a bit of latency from where. Recording and when the video goes live. Okay, it's audible, right? Quite a bit of latency where. Okay, let's go with the stream. So, I was reading this paper. This is my first time reading an ML paper. Not the first time. I read Attention is all you need, and BERT and few famous papers. But from this week, I am thinking of uh, making it an habit to read one paper per week and trying to implement the paper. So today I will start with deep residual learning for ImageNet. So I just few minutes ago I started reading the abstract and going through uh, few of the terminologies that this paper have that I don't know and trying to learn from it. So uh, deep residual uh, deep residual learning for ImageNet. It was written by Kevin He, Zhang Gui Zhang. I'm really bad with pronunciation, so sorry for that. And Xiaoying Ren and Zhang Shang, Microsoft researcher. You can uh, communicate with them using this mail. So till now, I understood that the deep neural network are quite difficult to train because deeper the layer, the gradient get uh, diminishes with each passing layer. So the researcher came up with residual learning framework. So residual learning framework that changes the layer with residual framework. So I was trying to read what is this residual framework and all that, and type type of ImageNet type in which dataset it was tested on and all that. And along with that, I'm also making some notes on the residual learning method. Ignore this part. And residual learning method, how it works, and all the overview. So first, I will try to get a bird's eye view of the paper, reading to the abstract, going through the figures and what metrics are used, and its conclusion. Then after that, I get an overview. I will try to go in depth in this paper. So along with reading the paper, I am also using notebook LLM to understand terms that I don't know. So I have already pasted the paper here, and I'm also looking at few terminologies like the top 5 the error metrics that what you use in this paper. So now I'm trying to understand this top 5 error evaluation. So let's see. So top 5 error. A metric that evaluates model performance by measuring the proportion of cases where the correct label is not included. Metrics that evaluate the model performance by measuring the proportion of cases where the correct label is not included. Among the top 5 prediction in large-scale multi-class categories. So this matrix is used in multi-class classification. Okay. Let's Firefox. We don't like the highlight of Firefox. It's a headache to use this. So it is used for large-scale multi-class classification. So let me do something. What was that? Down. I have a markdown tool. Forgot the name of that. It's been many days since I have used that. Let me use the text editor here. So top 5 error. What is it used for? Is for multi-class classification. Classification. Okay. Evaluates the model performance by measuring the proportion of cases where the correct label is not among the top 5 prediction. Okay. From this title, I am trying. What I understand is it has top 5 categories, and it measures how many of the prediction belong to only that categories. Okay. Top 5 evaluation metrics measure how often the correct class is absent from a model's top 5 prediction class. Metric that measures how often the correct class is absent. The correct class is absent. Okay, whatever the correct class of the image is, it is not present in the top 5 predicted class. What do you mean by top 5 criteria? How do you understand this top 5? Let's see. How do you know about this top 5? What's the top 5? It is especially useful in large scale image classification tasks with hundreds of thousands of categories, which are more flexible view of recognizing performance is often more informative than judging the model. Recognition performance is often more informative than judging the model by single high rank prediction. It is a more flexible view of recognizing performance. Performance is also, put it simply, it is allowing a student to write down 5 possible answers instead of just one on a difficult exam question. Even if the first choice is wrong, the model gets some credit if the correct answer appears somewhere in the top 5 guesses. Okay. Top 5 guesses, top 5 possible answers. One on a difficult exam question. Even if the choice is wrong, the model gets credit. Okay, so for what I understand is, so it goes through the model, say it's image of a butterfly, it goes through the model and it try to predict, even if it doesn't belong to the top 5 categories, it try to answer the question which category it belongs. Okay. right for me to understand top 5 represent the fraction of sample for which the correct class does not appear in the model's first likely prediction. Fraction of the sample. So which for which correct class doesn't appear in the model's 5 most likely prediction. Okay, so say I have bunch of sample and the correct class is not in the top 5 evaluation. How do you measure the top 5? Means what? My question is what represents the top 5 category? Uh, how do you take top 5 prediction? Means which classes are top 5 prediction? It becomes standard benchmark measure in ImageNet comparison. Becomes a standard benchmark measure in ImageNet era comparison. Okay, the basic idea of top K evaluation in a large multi-classification requires a model to get exactly one answer right. It can be overly strict for a reason. It is common to sort all classes by confidence score, probability, and keep only the top K candidate where K equal to 5. The resulting error rate is top 5 error. In other words, the metric asks whether the correct label is included among the top 5 most possible answers. Total number of samples correctly measured. Okay. Error rate. So it's how often gets prediction wrong. Error rate is a proportion of prediction in a classification model gets wrong out of all the prediction because it is simple to compute and easy to interpret. This is often more basic evaluation metrics for quickly checking how often a model makes mistake. If a model answers 100 questions and get 8 of them wrong, the error rate is 8%. In other words, instead of showing how often the model is correct, the metric tells how often it fails. Okay, error rate, rather than measuring whether it's correct, it measures whether it's wrong. Lower the error rate, better the model. Okay, error rate is a proportional prediction model gets wrong because it's simply compute and easy to implement. Okay, error rate obtained by checking whether the prediction is correct or incorrect, counting only the wrong prediction and dividing the count by total number of prediction. Sequential chance which each sample has clear ground truth. It provides one of the simplest summary of model prediction. A lower value means model has fewer mistake, higher value is more mistake. Okay, wrong by n, 1 accuracy. If total number of prediction is denoted by n, the number of wrong prediction by wrong, then the error rate is computed as wrong divided by n. For example, if a model gets 18 out of 20 prediction wrong, the error is 18/20. This can be interpreted as out of every 100 prediction the model gets 9 wrong. Okay, 1% accuracy. It has some relationship with accuracy. Accuracy is a proportion of correct prediction, whereas the proportion incorrect prediction. This means that accuracy goes up, error rate goes down, and the whole error it is quite trivial, right? So if it makes fewer mistake, it will make more correct prediction, and accuracy is just total sample divided number of correct prediction divided by total number of samples. You can think of them two ways to describe same performance. One perspective of correct, another perspective mistake. Or to watch out error rate, treat every mistake the same, so you cannot know whether some error rate or more close to it can make performance better than it really is when the data set is imbalanced. Yes, it's quite a problem in most of the cases. So imbalance data set can be quite harmful. For instance, of 980 out of 100 sample belonging to a model that predicts everything as normal would still have an error rate of 2%. This is why in practice safer to interpret error rate as fusion. Okay, starting but models is easier to do. Okay, I understand what error rate is. So when k equal to the result, that is number of classes. So I take the top 5 class and check how many times that the samples are wrong. I have to get some example to understand this properly. So suppose a data set has 100 contain 100 images. If the correct label is missing from the top 5 prediction for 8 of them, then the number of error is type. Okay, top 5 evaluated, top 5 accuracy 95, meaning that the model includes the correct number of labels. Why it matters? Top 5 error become a key metrics. Image rate, large data classification challenge. Okay, ImageNet large scale visual classification challenge, ILS PRC. Because the ImageNet affiliate 1000 object evaluating only one single on a single highest rank prediction can be harsh. So it takes an image and predicts out 5 categories, and after comparing the 5 categories, even if it doesn't belong to the 5 categories, is the 5 categories predefined, or what do you mean by top 5 categories? Top 5 prediction. Oh, it's model's top 5 prediction doesn't belong to the correct level, then then we calculate. Okay, now I get it. So okay, top 1 is a prediction whenever a single high scan, top 5 is lenient. Isn't leniency a bad thing? Because doesn't it make the error quite bad? Let's think about it later. So this is how it is calculated. Let me quiz myself with this. So let me go with Gemini. So I am trying stand top 5 error rate. Can you quiz my understanding of this topic? Should be right. Which one of the following best define the multiple? The average margin across error margin across 5 most frequently predicted class. The percentage of cases where the highest probability prediction is the ratio of the top 5 classes. The percentage of cases with the target level is not among the top 5 as well. Okay, I think that's the answer. Next, if you achieve an accuracy of 88%, top 5 accuracy means if among all the samples about 88% of them have predicted top 5 categories, and the top 5 categories belong to one of the labels, so then the corresponding it is 2 to 12%. Okay, which is mathematical relation of top 5 and top 5 is always true for same model and data set. Oh, there is also relation. So top 1 error rate and top 5 error is always true for same model. Okay. So top 5 error rate, is it 5 times? No, because if it was 5 times, wouldn't it increase the error? How could I understand that? So top 1 error rate, so you take a model, you take its prediction and compare with a single level. You compare the single level with one prediction. So if they match, then you are good to go, you are correct. And if it doesn't, You see, you take that, understand that. Let's first go with the formula. So, top one error rate, how will it go? Top one, top one would be error in one category prediction divided by your total, and top 5 is equal to error in 5 cat prediction sample. Right, okay. If I try to understand the first one, it's 5 times. So if it's 5 times 5 categories divided by 5, right? Or doesn't error is, how could you make this formula 5 times 5 into error? Wouldn't it be like just adding up the errors? You take the same error, you add it 5 times, but we are not adding the error 5 times, we are just taking the error and I don't think that's the correct answer. We should eliminate this. We are not adding the error 5 times, rather we are taking the error and checking its prediction, right? So would the error in 5 be greater than error in 1? Error in 1. Isn't it E1 quite strict? If one doesn't met, it gets eliminated, but you have 5 chances for error in 5, right? So wouldn't the error in 5 be quite less than error in 1, because we have 5 more chances? So I think C is could be the answer, and tower 5, I think C would be the correct answer. Okay. You can means, how could you uh, like, increase by power? I don't understand the relation. A model outputs the following probability: A 0.35, B 0. The ground truth is F. 1, 2, 3, 4, 5. How is the instance recorded? Top 1's error and top 5 error. Yes, because if it belongs to F, then it doesn't belong to. If it wasn't, if we use top 1 error to measure it, so it wouldn't be belong to category A, so it would automatically be counted in the top 1 error, right? So then after that, if it belongs to F, then it doesn't belong to A, B, C, D, the first 5 classes, so it would also be counted in top 5 error. Top 1 success, I think it's talking about the accuracy. So I don't think it will be counted in success, right? So I think it's top 1. Okay. Success. So it is outside the top 1 and top 5. So it belongs to top 1, top right? Why is top 5 often preferred over top 1 in a honey grading model? I really don't know the answer to this. I think I'm indifferent when I think about difficulty in choosing. Okay. if you have two very similar class, say an wolf and a fox, so it becomes quite difficult for model to differentiate between the two. How could I go with it? Let me see. Many image content multi-class object level that are visually similar and it artificially inflate the performance to make model appear more accurate than they are. I don't think any error rate will try to shouldn't it show the true performance. Less computation expensive, no, right? If you have a top 5 error, it's quite simple to compare with the one, but if you have top 5 error, you have 5 values to be calculated. But for top 1 and top 5 error, the all of the softmax and all that has to be calculated. We have to just compare the top 5, right? And for top 5, just we have to compare the top 5 with the level. It is expensive than top 1, but if we just have to compare the 5 values with a single level, so I don't think it would be quite, it will be constant, right? Standard optimization energy can only minimize top 5 visually similar to should be answer yes. Many impact content object or level that are visually similar. Yes, I read the same distinguish very similar breed of dog and some dogs. Yes, is right. So if even fox and wolf, they are quite similar. So fairly making a comparison for a model is quite different for even making fairly assessment. So we try to be more lenient. Class to class, the top 5 error rate for any model is, what is the top 5 error rate for binary class classification? Either belong to 1 or 2. How could they have top 5 error rate? Wouldn't it be 100%? Okay, 0%. Okay, aha! If you have a top 5 error rate, top 5 accuracy, yes, nice. Within the top 2, right? Yes, you can measure in binary class with that. How does increasing the number of classes in dataset affect the gap between top 1 and top 5 error rate? So from the if you saw the top 2 error rate, it's quite similar, right? So if you increase the number of classes, we have more classes to compare our prediction with, and if you have more classes, then if top 1 doesn't matches with any one of the category, but top 5 is quite lenient, so it has more categories to choose from. Typically decreases, the gap typically increases, it becomes harder, right? If you have only 1 and 2, so it becomes easy for model to predict, right? And for top 5 is always lenient, so I think the gap increases constantly as the gap is. Yes, right. Okay. Is the result of 1 error. Okay, it will be a top 1 error, but it will belong to top 5 success. It can be determined from softmax probability, right? Because softmax is the last most of the time softmax is the belongs to last layer, which help us give a probabilistic view of the log it's right. So the following mostly directly improve the model top 5 error rate without necessarily changing the top 1 error rate. I don't know about this residual connection. I don't know about this. Let's see the next question. We'll check it at last. Let's go back. What the answer of the okay. I think that would be all. Let's see. Solid progress. Keep going. Strand. Okay. I understand this error metric. So the in this paper we have an error matrix of 3.5% error rate, right? So that means after the prediction, only 3.57% of the samples didn't belong to the class it predicted. Okay. So top 5 error rate, right? So top 5 error rate. To understand what top 5 error rate is. What is this improvement? Eight times deeper than residual network. So it uses a network which is 8 times deeper than residual network. How do you or 28%? How is this measured? Let me take a break for a few minutes. After that I will be back with the stream. So let's stop the stream here for a few minutes. We will continue.